let's actually calculate some Laplace transforms. For these, we'll look at 3 examples, and I strongly encourage you to pause this video and try to calculate these Laplace transforms yourself before I work through the example. Now remember that the formula for the Laplace transform is the Laplace transform of a function f is the integral from 0 to infinity of e to the minus st times f of t dt. And for now, the only way we have of calculating Laplace transforms is using this formula. So pause the video and try, using this formula, try to calculate the Laplace transform of the function t. Okay, so here we go. The Laplace transform of the function t, using this formula, it's the integral from 0 to infinity of e to the minus st times f of t is just the function t in this case. Okay, and when we do this integral, we have to be careful with this upper bound infinity, right? What this really means is we're going to take the limit as we need a new variable name, how about a? Limit as a goes to infinity, and then the integral is from 0 to a, right? That's really what this means. So I won't write out this limit every time, but just keep in mind that when we see this infinity in an upper bound, this is really a limit. So we're going to have to calculate some limits at infinity here. Okay, with that said, to do this integral, we have to do integration by parts. So, right, integrate the exponential part and differentiate the t part. So we get minus 1 over s e to the minus st times t, and this is from 0 to infinity. And remember, this 0 and infinity, these are t values. Because this integral was with respect to t, these bounds are t values. Okay, plus integral 1 over s e to the minus st times the derivative of t, which is 1, dt. And this integral is also from 0 to infinity. Okay, now, so we get minus 1 over s. Now, to evaluate at these bounds, remember the bound for infinity, this is really a limit as t goes to infinity. So what we need to do is ask ourselves, what does this function do as t goes to infinity? Well, this t part right here, as t goes to infinity, this t goes to infinity. As t goes to infinity, this exponential part, well, whether this goes to infinity or to 0 depends on what s is. If s is positive, then we are getting e to a negative, this exponent is tending towards infinity, negative infinity, and so this part will go to 0. But if s is negative, then we have e to a negative times negative, and that's positive, so this, as t goes to positive infinity, this exponential would be going to e to the positive infinity, and that's positive infinity. So the upshot of this is s can't be negative, right? For this whole thing to make sense, s has to be positive. So whatever function of s we end up writing down here, for it to be defined, s has to be positive. Okay, but if s is positive, we have an exponential going to 0, we have a polynomial going to infinity, the exponential wins, right? If you need to, you can use L'Hopital's rule to determine that the exponential wins in this competition between the exponential decay and the polynomial growth. But this limit, so this limit is 0 by L'Hopital's rule. Okay, minus, and now we use the bound at 0. And, well, when you plug in 0 for t, this whole thing comes out to be 0. So this first term actually doesn't end up contributing anything. Okay, plus, and now we need to integrate all of this. So we get minus 1 over s squared times e to the minus st. And again, we need to evaluate at our bounds here. Okay, so remember all of this stuff was 0. So minus 1 over s squared times, now take a limit as t goes to infinity. Well, again, for this limit to be defined, for this limit to converge and not just fly off to infinity, we have to have s being greater than 0. And if s is greater than 0, then this exponential, when t goes to infinity, this exponential goes to 0. So we get 0 minus, and now plug in 0 for t. Well, you get e to the 0, and that's 1. So the minus signs cancel, we get 1 over s squared. So the Laplace transform of the function t is 1 over s squared. All right, let's try another one. How about the Laplace transform of e to the at, where a is any constant? So pause this video and see if you can work it out on your own. The domain of your function might depend on a. Remember, in our last example, we found that the domain of our Laplace transform function was only positive s values. So in principle, the domain of this Laplace transform might depend on what the constant is. So pause the video and try to work it out for yourself. Okay, let's work out the Laplace transform of e to the at. So just using the formula for the Laplace transform, this is the integral from 0 to infinity of e to the minus st times e to the at dt. And I don't know about you, but when I see these two exponentials being multiplied, I want to put them together. That's a prerogative that we have for exponentials. So e to the minus st plus at dt. And now it looks like maybe factoring the t out in that exponent might be a good idea. So integral from 0 to infinity of e to the, let's see, a minus s times t dt. And now we can integrate this directly. So remember, t is the variable for this integral. S and a both act like constants for this integral. Integral from, so 1 over a minus s times e to the a minus s times t from 0 to infinity. Okay, so this is 1 over a minus s. We got e to the a minus s. And we're plugging in our bounds, so I'm going to write infinity here, but remember, this infinity is really a limit. So we're going to have to think about what happens to this exponential as t here goes to infinity. Minus e to the 0, and e to the 0 is 1. Okay, so now let's think about this limit. Well, so e to the a minus s times t. If this exponent is positive, if a minus s is positive, then we have an exponent that's growing to positive infinity as t goes to infinity. So in that case, this whole thing would blow up to infinity. And we don't want that to happen, right? We're looking for a function of s that is defined. So what happens if a minus s is less than 0? If a minus s is less than 0, then this coefficient in the exponent is negative. T is going to plus infinity, so the whole exponent is going to negative infinity. So e to the negative infinity, that's tending toward 0. And so that's well defined. So this whole thing is defined when a minus s is less than 0. In other words, when s is bigger than a. So the domain of our Laplace transform function is right here. S has to be bigger than a. So if s is bigger than a, then this limit is 0. And we get 1 over a minus s times, right here we had a minus 1. So that's 1 over s minus a. And this is when s is bigger than a. So this is the Laplace transform of e to the at. All right, fair enough. look at one more example. As usual, pause the video and try to work this one out for yourself. Okay, so Laplace transform of e to the t squared is integral from 0 to infinity of e to the minus st times e to the t squared dt. Well, we can put these exponentials together, so integral from 0 to infinity of e to the t squared minus st dt. And, well, let's see. First of all, I'm not sure how to get an antiderivative of this, but let's just think about when this would be defined. So this exponent function, t minus st, it's going to look like this for some value of s, right? So this is on the t-axis, but this quadratic, t squared minus st, it has a 0 at 0, and it has a 0 at s, right? So eventually, when t gets big enough, this exponent goes off to plus infinity. And when that happens, this integral will also go to plus infinity. So this integral is always infinite. It doesn't matter what s is. So that means that this Laplace transform is never defined. So it was kind of a trick question here. So the point of this example is that we really have to be careful about the kinds of functions that we take Laplace transform of, because not every function has a Laplace transform.